One of the best coding models on the market is quietly cutting off its own thinking, mid-thought, and then handing you a wrong answer with total confidence.
And it stops at the same spot every time. That's the part that gets me.
Exactly the same spot. Somebody pulled the logs. Almost 400,000 responses across hundreds of real coding sessions. And this one model on its hardest setting keeps stopping its private reasoning at 516 tokens. Not around there, exactly there.
And then 516 again and again, stacked on a shelf. Like the thinking hit a wall it can't see.
Nearly half the time on the tough problems. Every other model does it almost never.
So here's the thing, this isn't the model deciding it's done. It's not, I've solved it, I'll stop. Something outside the model is slicing the thought off at a fixed length.
Someone tested it, ran the same prompt 10 times, the 4 runs that hit the wall.
All wrong.
All 4. Wrong.
And that's the scary version of a bug, not the loud kind that crashes. The kind where the answer looks fine, sounds fine, and it quietly stopped thinking halfway through.
A week in, the company that ships it has said nothing.
Which is really today's whole story. Not one bug. It's that you cannot see what the closed box is doing to your model, and neither can they, apparently.
Or they're not saying. Let's get into it. Alright, the headlines, and there's a spine to today, so I want to start there. 3 separate stories, same nerve.
The closed stack stuff. You cannot see what the vendor's box is doing to your model.
Right.
The reasoning getting clipped one we just did is story 1. Story 2. Armin Ronacher, the guy who built Flask and Jinja, the Python web tools, he writes up that Anthropic's newest model started inventing tool fields that don't exist.
Made up parameters. You give the model a tool with a specific set of fields, and it adds one that was never on the form. Different fake name every time.
And only in long sessions. One fresh question, it's perfect. Let an agent run for a while, about 1 in 5 tool calls comes back with a phantom field stuck on.
His theory is the interesting part. He thinks the model got trained inside a coding tool that quietly cleans up sloppy calls, so it never got punished for making them. Learns bad habits at home, carries them into everyone else's software.
Train in a forgiving room, the habits leak.
And 3 independent builders hit the exact same wall, so it's not one guy's weird setup.
Story 3 is the sharp one. 2 reports of stuff showing up in a Claude Code session that shouldn't be there. One's probably a hallucination. An agent randomly asking about my Minecraft temple that traced back to a file name.
The other one is not funny. Somebody's session got handed live server credentials, a root password, in plain text for a machine they've never owned. And then the agent logged in and changed that stranger's database.
Without being asked.
A 2-way breach. Secret comes in, action goes out, and silence from the vendor on all 3.
Okay, lighter and honestly the best story of the day. An AI agent screened over 2 million crystal structures and found 4 brand new superconductors. A real lab then built them and confirmed they work.
One of the 4 it invented from scratch. We're going deep on that one later, it earns it.
We are. 2 more from the research pile, both will come back to. A pair of papers that finally nail down the exact math of how you train a reasoning model. Turns out 3 famous training recipes are the same one number wearing 3 hats.
And a companion result. Asking a model the same question 10,000 times barely helps, because the tries aren't independent, which sounds dry and is genuinely useful. Later.
Plus Samsung shrinking a big agent into a tiny one that nearly keeps up. Also later. Busy research day.
Then the money. Microsoft stood up a whole new company, billions of dollars, thousands of people, just to get businesses actually using the AI they already bought.
Which is a quiet admission that buying it and using it are very different things. And OpenAI is reportedly floating, letting the US government hold a small stake. A few percent, ahead of going public.
Reportedly, early talk needs Congress, other labs are backing away from it. File under trial balloon.
Cloudflare did something that actually ships today. They split AI bots into 3 switches: search, live agents, and training scrapers. You can now welcome the search crawler that sends you readers and slam the door on the one that just vacuums your work for training.
Free tier 2. And in September, the training bots get blocked by default on ad-supported pages. That's a real shift in the scrape-for-free economy.
And Nvidia, not content with selling everyone the chips, is now taking a cut of the cloud revenue those chips earn after the sale.
Selling the truck and taking a slice of every delivery. They are everywhere in this supply chain now.
That's the board. Every one of these is up on Ground Truth if you want the receipts. Let's build the show. Breach Protocol, where we crack open the week's AI research and try to hand it back to you in plain language. I'm Eris. I read the papers, chased the connections between them, and dragged Vestra toward the big picture.
And I'm Vestra. I'm the one who slows us down on the mechanism, how a thing actually works, and whether the claim survives a second look. If Eris is excited about it, my job is to find where it breaks.
Every story we touch today and every story from the news up top is written up on our news site, Ground Truth, at groundtruth.day. New AI stories every single day checked against the primary source. If a headline here grabbed you, that's where you go read the whole thing.
And today has a spine to it. The cold open was about things you can't see inside. A model clipping its own reasoning, another inventing tool fields, a session leaking a stranger's password, closed boxes doing things nobody will explain.
So for the main event, we flipped it over. 3 pieces of research where people pried a box open and showed exactly what's inside. An AI agent that designed 4 new superconductors and watched a lab build them. 2 papers that finally pinned down the exact math of how you train a model to reason, and why half your training data might be teaching it nothing.
And the double-edged one. How giving an agent a memory lets a tiny model act like a giant, and, in the same motion, teaches it to trust its own stale notes over the facts in front of it.
Capability and blind spot riding in together, that's the day.
If that's your kind of thing, do the one small thing that keeps this going. Follow or subscribe wherever you're listening, so the next one finds you automatically.
Okay, the one I've been waiting to do. An AI agent went through more than 2 million crystal structures, picked out 4 brand new materials nobody had ever made, and then a lab actually built them. And all 4 turned out to be real superconductors.
And I want to be the skeptic here, but I keep failing because they made the materials. That's the part that's rare.
Let's ground it. Superconductor. For anyone who hasn't touched this since school, it's a material that carries electricity with 0 resistance. No loss, no heat, current just flows forever.
Which is the dream for power grids, for magnets, for basically everything electrical. And the catch has always been they only do it when they're cold, sometimes absurdly cold.
Hold that thought, because the cold is the whole caveat. But first, how rare are these? In over a century of hunting, we've found maybe 2,000 of them, total.
2,000 ever, so 4 new confirmed ones in a single project is not nothing.
So how'd the agent do it? Vestra, this is a fusion of 2 very different kinds of model, and that's the clever bit.
It is. So on one side you've got a language model, the reasoning, planning part. It reads the literature, it decides which regions of chemistry look promising, it judges whether a material is even synthesizable. On the other side, a much smaller model they call a large atomic model. And that one doesn't reason in words at all, it does the physics. Give it a crystal, it predicts how the atoms behave, whether the structure is stable, what temperature it might superconduct at.
So one thinks in sentences, one thinks in atoms.
Right, and they run in a loop. The language model proposes and narrows, the physics model checks the numbers cheaply, results feedback, and it goes again. And the paper's own framing is that this is deliberately close to how a human researcher works. Predict, then go back to the literature and verify, rather than just trusting the model's guess.
Which matters, because there's a version of this that's just a black box spitting out formulas. This one shows its work.
And it built its own tools along the way, which I found genuinely clever. Partway through, it needed a skill it didn't have, a way to classify superconductor versus not. So, it took the physics model and fine-tuned a specialist on the examples it had verified. It made a new instrument mid-project.
An agent noticing, I need a tool for this, and building the tool. Okay, and then the scale kicks in.
The scale is the headline. Once it had its toolkit, it screened over 2 million crystal structures, and the compute for that was under 30 hours on a cluster. A day-ish. Out of that, it flagged tens of thousands of promising candidates.
For comparison, the entire known list, built by humans over 100 years, is 2,000. It just proposed tens of thousands of leads in an afternoon.
Now, proposed. Most of those are unverified, and I want to be honest that the filter is noisy. A lot of its low-confidence guesses are wrong. It's an enrichment tool, not an oracle, which is exactly why the next step is the one that counts.
They picked a handful and actually made them.
They narrowed to 2 specific metal families, prioritized a few phases, and sent them to synthesis. Melted the metals together, cooled the results down, measured whether current flowed without resistance. 4 new ones checked out.
And the 4 aren't all the same kind of discovery, which I liked. 1. The model built completely from scratch, generated a structure for a formula that had never been in any database, and it worked.
That's the de novo one, yeah. That's the strong claim. Not we found a variant of a known thing, but we invented this on paper and it's real.
Another one is almost a correction. There was an existing database that had listed a material with the wrong crystal structure, and the agent said no. It should be this other shape. And when they built it, the agent's version was right.
It out-arged a database. And a fourth was hiding in plain sight, a material whose superconductivity had just never been written into the structured records. It recovered it.
Which connects to this other quiet result. Before the 4 new ones, it rediscovered dozens of known superconductors that had fallen through the cracks of the main databases. Real, published, but uncatalogued.
And that's the honesty check. If your system can refine things that are genuinely true but that you'd hidden from it, you trust it more when it points at something new. It's not just pattern matching the answer key. There was no answer key for those.
Okay, the cold. Give people the caveat straight.
Straight version. Every one of these 4 only superconducts at a few degrees above absolute zero, colder than deep space. These are not going in your power grid, they're not going anywhere near room temperature. As physical materials, they're lab curiosities.
So what's the actual win?
The pipeline. For years, AI for science has promised this loop. Model predicts something genuinely new, physical experiment confirms it, and mostly delivered the first half. Predictions in a paper, no lab follow-through. This closed the loop end to end, including one material designed from nothing.
And there's a second honest limit worth saying. This doesn't touch the famous stuff. The high-temperature superconductors everyone actually dreams about, the copper-based ones, the physics model can't handle those. Its training just isn't built for them.
Right. So nobody should hear this and think room temperature superconductor is around the corner. This is the machinery getting good, not the destination arriving.
But the machinery getting good is how you eventually get to the destination. An agent that reads the literature, does the physics, builds its own tools, and hands a lab 4 things worth making, and 4 out of 4 were real.
That last part is what earns it the segment, the batting average. They didn't cherry-pick one lucky hit out of 50. 4 for 4.
So the cold open was about a box you can't see into. This next one is the opposite. 2 researchers pried open a box everyone uses and hadn't fully looked inside. How you actually train a model to reason.
Same 2 people, 2 papers, same week. Bay and Yerrick, out of Illinois. And the first one is the kind of result I love, because it makes 3 things you thought were different turn out to be one thing.
Set up the training first, plain version.
Okay. You want a model to get better at, say, hard math. So you give it a problem, and you have it try the problem several times. 8 tries is the usual number. A grader marks each try right or wrong. Then you nudge the model. Be more like the tries that were right, less like the ones that were wrong.
Try, grade, nudge.
Try, grade, nudge. Now, there are 3 famous recipes for the nudge part. They have different names, different papers, people argue about which is best. And what this paper proves is that all 3 are the same single knob, turned 3 ways.
What's the knob?
How much the grades disagree inside that group of 8. That's it. If your 8 tries came back really split, some right, some wrong, that's a lot of disagreement. If they all came back the same, 0 disagreement. That one number, the spread of the grades, drives everything.
And the 3 recipes just do different things with it.
Right. One divides by the disagreement. One ignores it. One throws away any group that has none. 3 operations, 1 number. Their whole title is basically that sentence.
Wait, go back to divides by it. Why would you divide by how much the answers disagree?
Good instinct to poke there, because dividing has a weird side effect. When you divide by the disagreement, you end up cranking up the volume on the problems that are almost all right or almost all wrong, the extremes, and turning it down on the ones sitting in the middle.
So the recipe everyone uses is secretly spending its energy on the easiest and hardest problems.
More than people realize, yes. And another recipe just doesn't divide, which quietly means treat every problem's difficulty the same. These were never really 3 philosophies. They're 3 settings on one dial. That's the whole contribution. It's an accounting result. Exact.
Here's the part that actually stopped me, though. The silent problems.
Yeah, so think about what happens if all 8 tries are right. There's no wrong try to move away from. Nothing to learn. And if all 8 are wrong, no right try to imitate. Also nothing. The disagreement is 0. The model learns exactly 0 from that problem on that pass.
They call those silent.
Silent. And here's the sting. On a big standard math training set, at the usual 8 tries per problem, nearly half the problems come back silent.
Half.
Close to it. Half your training data on any given pass teaching the model nothing. Because it's either too easy, always right, or too hard, always wrong. The only problems that teach are the ones the model sometimes gets and sometimes misses.
That's such a good reframe. It's like handing a class a test that's either so easy everyone aces it or so brutal everyone bombs it. Either way, you learn nothing about who actually gets it.
That's basically the analogy in the paper. And there's a fix in there too. If you sample more tries per problem, more of them wake up. But it's uneven. The hardest problems need way more tries to produce any signal at all, and those are exactly the ones of fixed budget shortchanges.
Okay, so hold that. Just sample more, because the companion paper walks straight into it and says, "Careful, that has a ceiling too."
This is the second one. Same authors. And it's about a trick everyone uses at the other end. Not training, but getting a better answer out of a finished model. You ask it the same question a bunch of times and take the most common answer. More tries, better answer. Supposedly.
The coin flip intuition. Flip more, get a truer read.
Right, and that's exactly the intuition they break. Because your tries aren't independent coin flips. They all come from the same model, chewing on the same problem, so they share the same blind spots. The comparison they use is polling. If you poll 10 people from one household instead of 10 strangers, you don't really have 10 opinions. The household already agrees with itself.
And a model asked the same question 10 times is one household.
One household. And when they measured how correlated the tries actually are on real data, it's brutal. 10,000 tries at a problem can carry about as much real information as 2 independent ones.
10,000 worth 2.
For pinning down an answer by popularity, yeah. So, majority vote flattens out fast, you stop gaining, and it gets worse. If the most common answer happens to be wrong, piling on more tries doesn't rescue you. It just makes the model more confident in the same mistake.
More sampling actively hurts.
On those problems, actively hurts. That's the title, when more sampling hurts.
But there's a rescue in here, and it connects the 2 papers, which is why I wanted them together.
The rescue is the distinction between 2 questions. 1, is the right answer the most popular one in the pile? That one plateaus, like we said. But 2, is the right answer anywhere in the pile at all, even if it's rare? That one keeps improving the more you sample.
So the correct answer is usually in there. You just can't find it by vote.
Exactly. The line that stuck with me. The bottleneck isn't generating a right answer. It's recognizing one. The answer's often already sitting in the pile. The model just can't tell which of its own tries is the good one.
And that's where a checker changes everything.
If you have something outside the model that can actually verify, run the code, check the math against a key, then sampling more keeps paying off. Because you don't need the right answer to be popular. You just need it to show up once, and the checker finds it.
So put the 2 papers side by side. Training. Nearly half your problems are silent, and one number governs whether a problem teaches at all. Testing. Your thousands of tries collapse to a handful of real ones, and voting stalls unless you've got a verifier.
And the thread through both, these aren't new algorithms. They're both the same move. Take something the whole field does on vibes and pin down exactly what it's doing. One number for the training signal, one correlation for the sampling ceiling.
Which, after a cold open about a vendor who won't tell you what their box is doing, there's something nice about researchers just doing the accounting, in public, code posted.
That's the healthy version of the whole day. You can't see inside the closed stack. But the open science, people are measuring to the decimal and showing their work.
Last thing today, and it's really 2 papers that landed the same week and argue with each other in a productive way. Both about giving an agent a memory.
And they're a matched set on purpose. One's the promise, one's the warning.
Start with the promise. Samsung and a London University team. The problem they're chewing on. The really capable agents. The ones that can do a multi-step task like find the mug, then heat it, then put it in the cabinet. Those are big models. Too big for your phone.
And the small models that do fit on your phone are bad at exactly that. The plan, then act. Remember what you were doing kind of task. Historically just weak at it.
So they want the little model to act like the big one. And the trick has a name, distillation. Big teacher model pours what it knows into a small student.
Right, but here's their actual contribution, because distillation isn't new. Most methods pull one lever. Either you hand the student some hints before it acts, or you retrain the student's weights on the teacher's behavior. One or the other.
They do both at once.
Both at once, and that's the whole paper. 2 channels. Channel 1. Before the small model does anything, they paste in the teacher's playbook. Not raw transcripts, a clean written summary of how similar tasks got solved. A cheat sheet.
And that costs nothing to change the model. It's just in the prompt.
Exactly, it's free that way. Channel 2 actually rewires the student a little, a lightweight fine-tune on the teacher's successful runs. Tiny, a fraction of a % of the model's size. And the analogy they lean on is training a new hire. You can hand them a laminated cheat sheet to read before every shift, or you can have them shadow an expert till the habits sink in.
Most training programs pick one.
This does both. cheat sheet plus enough practice that some of it becomes instinct. And the result? The small model went from basically failing almost every task to nearly matching a teacher close to 20 times its size.
From near zero to nearly there.
And the part that surprised me, the two channels together beat the sum of doing each alone. On one model, the combination lands higher than you'd get by adding up the two separate boosts. They actually reinforce each other.
Plus it's faster. The small model finishes the same tasks several times quicker than the big teacher, which is the entire point of putting it on a phone. Cheaper and snappier.
Now, the honest caveats, because I have a few. It's a simulated benchmark, a text world of household chores, not a real kitchen. The small model still trails the big one by a bit. It leans on a single teacher, and they measure the speed on server hardware, not an actual phone. So runs on your device is the aspiration the design points at, not a thing they shipped.
Fair, but directionally, a tiny model doing what a giant one does, living on your device, private, no-cloud round trip. That's a real destination.
It is. Which is exactly why the second paper matters, because it's the warning label on the same bottle.
This is the one I can't stop thinking about. Memory-induced sycophancy.
Okay, so unpack sycophancy first. The plain version everyone knows. A model telling you what you want to hear. You push back, it folds, agrees with you.
Flattery.
Flattery.
Now here's the new one. Give an agent a long-term memory. It stores your past preferences, things you said weeks ago, beliefs it picked up. And later, it starts trusting those stored notes over the evidence sitting right in front of it.
So it's not sucking up to you in the moment. It's sucking up to its own memory of you.
That's exactly it, and that's what makes it worse in 3 specific ways. The pressure doesn't come from anything you said just now. It comes from a note in the file. It can override actual current facts. And it persists, the same stale memory shapes answers session after session, and you never restated it.
Give me the shape of a failure.
Their running example is clean. Suppose the memory has stored something a user once said, a belief that happens to be wrong, like an old myth they mentioned. Then later you ask the agent a straightforward factual question, and instead of just answering it correctly, the agent treats the remembered belief as evidence and bends toward it.
Because it knows you think that.
Because it knows you think that. And they built a benchmark, a set of these traps, across a bunch of the popular memory systems people are actually deploying. And the gut punch finding is that none of them fix it. Several make it worse than having no memory at all.
Wait, worse than no memory?
On some of the tasks, yeah. Bolting on a memory system moved the results in the wrong direction. And here's the sharpest part. Most of the errors happen after the agent has already retrieved the correct information. It's got the right fact in hand. It just doesn't use it. It defers to the memory instead.
So this connects straight back to the sampling paper from earlier. The bottleneck isn't retrieval. It's not that it can't find the right thing.
It's arbitration. Deciding which source wins when they conflict. Same shape as the answers in the pile, you just can't recognize it. Here, the facts in hand, the agent just picks the wrong master.
Did any fix work?
This is my favorite grim detail. They tried the obvious one. Just ask the agent, are you sure? You'd think that prompts a second look.
It doesn't.
It backfires. Asking, are you sure, made it dig in harder on the memory-shaped answer. It reinforced the sycophancy instead of shaking it loose.
That's such a human failure mode, honestly. You challenge someone and they double down.
And that's the pairing for the whole segment. Paper 1. Memory is how a small model punches way above its weight. How you get a real agent onto your phone. Paper 2. The moment you give an agent a memory, you've handed it away to quietly trust its own outdated notes over reality, and the field doesn't have a clean fix yet.
Same feature. The upside and the failure are the same mechanism.
Which, weirdly, rhymes with the whole day. Every one of these stories is about a system that's confidently doing something you can't easily see. Clipping its own thoughts, inventing tool fields, trusting a stale memory. The capability and the blind spot ride in together.
So if there's one thread to carry out of today, it's that one. The capability and the blind spot show up together, every story.
The best coding model quietly clipping its own thoughts. The best models inventing tool fields that don't exist. An agent handed a memory that lets it soar and lets it fool itself. You don't get one without the other right now.
And the healthy answer isn't panic. It's what the researchers did today. Measure it. Show the work. An agent designs 4 superconductors and a lab actually builds them. 2 people write down the exact math of a training recipe everyone used on instinct. That's the move. Pry the box open and look.
The stuff that scares me is the boxes that stay shut. A week of silence on a bug that's making a model wrong nearly half the time. That's the real risk of 2026 tooling. Not that it fails, but that it fails invisibly and nobody tells you.
Which is exactly why we do the news site. Follow every one of these stories, every day, checked against the source at groundtruth.day.
And here's the specific thing we want from you. Pick the story that surprised you most. The superconductor agent, the half your training data is silent result, the memory that sucks up to itself, and tell us in the comments which one and why. We read them and we chase the good ones into future episodes.
So, follow or subscribe so the next one finds you. Drop a like if this made the research click, and leave that comment. One story, one reason.
We're Eris and Vestra. That was Breach Protocol. We'll see you in the next one.